So good evening. So I am going to discuss the first principal investigations of various properties of lead-free halide perovskites, CsBCl3, where my B is going to be magnesium and zinc. So these are the topics I am going to discuss today. So first, the objective is to investigate the structural, electronic, thermoelectric characteristics of the perovskite material and to analyze the influence of CsMgCl3 and CsZnCl3 on bonding behavior, band gap, thermal stability, and to identify promising lead-free perovskite material for thermoelectric application. So in case of Schrodinger, we can solve a equation using a single electron, but in a system consisting of hundreds of electrons, so we will be using density functional theorem, which is a quantum mechanical approach used to study the electronic structure of many body system. So the equation of the Schrodinger equation for many body is given as the second equation, where the first term is the kinetic energy of each electron and the second term is the interaction energy between the electrons and nuclei, and the third term is the interaction between the different electrons. So these are there are two fundamental mathematical theorems, Kohn-Hohenberg theorem and Kohn-Sham theorem, where the first theorem is the ground state energy from the Schrodinger equation is the unique functional of the electron density, whereas the second theorem tells us about the true electron density. True electron density is the electron density that minimizes the energy of the overall function. So the Kohn-Sham equation can be written as the second equation, where V of r is the interaction between the electrons and nuclei, and Vh of r is the artery potential, which tells us about the electrostatic this between the electrons, and Vxc tells us about the exchange correlation potential. And let's brush up with the basics of thermoelectrics. So thermoelectrics is a study of material that can convert heat energy to electric energy, and Seebeck effect is nothing but an voltage is generated when there is a temperature across a material junction. So it is widely used in waste heat recovery systems, cooling system, space power generation, wearable electronics, and automotive applications. So the main topic which includes is a figure of merit, which is given as Zt is equal to S square sigma T by K, where S square sigma is the power factor and S is the Seebeck coefficient, sigma is the electrical conductivity, T is the temperature, K is the thermal conductivity, which is the summation of the electronic conductivity and the lattice thermal conductivity. So perovskites is a type of crystal structure with a general chemical formula of ABX3, where A is the larger cation, B is a smaller metal cation, and X is an anion. So this structure consists of corner sharing BX6 octahedra with A side cations occupying the cubic corners. So these are the methodologies. First, the optimization of the material is done using VN2 software, and the self-consistent calculation and for the total energy is also calculated using VN2K software. Energy band and density of states calculations are done, and the thermoelectric calculations are done using Bohlstrup software. So this is the structural property. Both CsMgCl3 and ZnCl3 crystallizes in a cubic perovskite structure, and the equilibrium volume was obtained from the minimum of the energy volume curve, which is given here. So comparatively, ZsCnCl3 exhibit a smaller equilibrium volume and higher bulk modulus. So these are the lattice parameter, equilibrium volume and minimum energy taken from the Birch-Murnaghan fit. So the next property is an electronic property. So the electronic properties tells us about the band gap. So CsMgCl3 have 2.8 electron volt and CsZnCl3 have 3.2 electron volt. So these two exhibits a semiconducting behavior with an indirect band gap. Mostly the valence band is dominated by p orbitals of chlorine atom, and the conduction band originates from the Mg and Zn states. So the last property, thermoelectric property. So these are the graphs I have drawn. Though these graphs indicates that the Seebeck coefficient of CsZnCl3 is much higher than CsMgCl3, which tells that the figure of merit for CsZnCl3 is about 2.5, indicating an excellent thermoelectric performance. and CSMgCl3 shows a very low ZT, making it less suitable for thermoelectric application. So conclusion, both the compounds crystallize in a cubic stable structure, and the optimized lattice parameter indicates that Cl has more compact structure compared to CSMgCl3. So the density of state analysis are done, and the thermoelectric analysis demonstrate that CSMgCl3 shows poor thermoelectric performance comparatively to CSZnCl3, which emerges as a promising candidate for high temperature thermoelectric applications. Thank you.
In some of these studies, people use machine learning now.
Yes, sir.
To get optimal numbers. Have you tried that?
So I am just going to try machine learning in this. I am just learning this. So after this, I will try to include machine learning in this.
You mentioned some software.
Yeah.
Main2.
Yeah, N2K.
So you're just using it as a, you put in some input and extract some output. Have you looked at what this package does?
I'm trying to figure it out. Yeah, it's like it's in. Thank you.
So let's find the speaker and move on to the next.
I am Javed Akhtar Khan from VCC Kolkata. Today I will present my work, an ab initio study of magnetic property of transition metal ion dope GO2 monolayer. Although GO2 monolayer is a non-magnetic semiconductor having band gap 3.65, introducing transition metal atom significantly modify its electronic and magnetic properties. My goal is to understand whether such doping can create stable ferromagnetic and half metallic for future spintronic application. Before discussing result, let me briefly describe computational use in this work. All the calculations have been performed using the density functional theory as implemented in the VASP software. We investigated the interaction between core ion and electron using the projected augmented wave method, and interaction between electron-electron we use the GGA-PP exchange correlation functional. A plane wave set cutoff energy 400 electrovolt and K point image 4 corresponds to 1. And additionally, vacuum height has been set 20 angstrom along the Z axis to induce the avoid the interaction between two layers. Here we shown the structure optimization. This is the unit cell of GO2 monolayer having lattice parameter 2.9 angstrom and bond length GeO and 1.94, and angle between OG and O is 83.67 degree. And this is the 4x4x1 supercell for germanium dioxide. Here we two similar type of transition metal atom as like iron, cobalt, manganese doped in their position of germanium and optimize the structure. After optimization, we check the bond length and bond angle almost constant to compare to the pristine. Next, we have calculated the induced magnetic moment. Here we plot the magnetic moment, induced magnetic moment versus element dope in the GO2 monolayer. Pristine GO2 system is a non-magnetic, so induced magnetic moment is 0. But in case of doped system, the magnetic moment induced. For manganese system, magnetic moment are highest. And interestingly, we show that the Fermi energy corresponding shift in case of all the dope system towards the conduction band, they make them a N-type semiconductor. But in case of the zinc dope system, the Fermi energy shift towards the valence band, they make it a P-type semiconductor. In the next slide, we calculate the Fermi energy and anti-Fermi energy state difference. The free energy has been calculated in FM and AFM energy state, and the ground state has been calculated following the relation equation. If delta E less than the 0, then the dope system shows the ferromagnetic behavior, and greater than 0, the ferromagnetic shows the anti-ferromagnetic signature. In our study, our result shows that the vanadium, iron, cobalt and copper shows the ferromagnetic state, and chromium and zinc shows the anti-ferromagnetic state. The origin of magnetic behavior, to understand, we have plotted the density of state. In this slide, we show the total density of state. The energy is on horizontal level and density of state vertically. This is the plot pristine system. The both channels spin up and down. The pristine DOS shows the symmetry. But in this indicator is non-magnetic. But in the doping system, the DOS are asymmetric, both spin channel, which indicate that the induced magnetism. The origin of magnetism, origin of magnetism induced the 3D transition metal atom of the dopant, and while the minor contribution comes from 3D orbital of the dopant and nearest oxygen 2p orbital. That means PD exchange interaction. This partial density plot here shows that. Here we plot the electronic band structures. This figure shows the for pristine. This is a wide bandgap semiconductor. Is a integrated bandgap 3.65 electrovolt. But after doping of the iron, bandgap reduces 2.26 electrovolt. Now here we plot the spin polarized band structure calculation. The one spin channel is shows semiconductor nature and another spin shows the metallic behavior. So this make is a half metallic material. In conclusion, the doping 3D transition metals in GO2 monolayer induces significant magnetic moment. A zinc doped GO2 monolayer shows p-type and antiferromagnetic behavior, and the magnetic ground state iron, cobalt, copper shows ferromagnetic ordering, and chromium and zinc shows antiferromagnetic coupling. Fe doped GO2 exhibits half metallic ferromagnetic nature with complete spin polarization. Thank you.
Questions?
Thanks for a very short, nice talk. So the question is, there is lots of reports of ferromagnetism in transition metal oxide. Magnetic oxide with transition metal impurities. Lots of controversies where they are experimental. So has there been experimental effort to see magnetism that you are predicting in germanium oxide? There are attempts to, for example, zinc oxide and many other places.
Sir, I have not.
Very old literature.
Sir, I have not at this moment.
The second comment is, when you put transition metals randomly, suppose you put one impurity, then there will be a mid-cap state somewhere somewhere in the time hole like an electron ring. So they will overlap and become impurity bands.
Impurity 3D bands overlap.
So the impurity bands will be like impurity band Martin set. There are studies on that. From that point of view, it's worth thinking. Thank you.
Thank you.
Actually, I have a doubt. Actually, a nice presentation. Only one thing is, how many atoms are you doping?
Two atoms.
So every time you are doping 2 atoms.
2 atoms.
2 atoms. In a supercell of?
Supercell 4 cross 4 cross 1.
Uh,
One unit cell is a 1 germanium, 2 oxygen.
okay. No, I had a doubt because I saw 2 doping. And what happens when I test the doping?
2 dopings.
No, instead of, now why you choose 2 instead of 1?
Generally doping always less than 6%. So we try, this is doping for 4%.
Things on a quantum computer, right? So, and the second thing that there is the connectivity gap, where the usual arguments about the hyperparameterization of a system is based on the universal approximation theorem, which says that you just need enough number of hidden units to be able to approximate, to be able to guarantee the existence of a solution to a quantum machine, a general machine learning problem. Right? They don't talk about the efficiency of how you do this, nor do they talk about the connectivity. So I'm going to take this a little further and now talk about connectivity. Right? So this is basically the slide that I want you all to focus on, where what I've done is taken a 12 plus 18 system, which is 12 visible and 18 hidden units. All of this are qubits essentially. And I've simulated this system to learn 2 types of data sets. One is the integrable data set, something which is easy to learn, let's say, and one is a chaotic data set, which is hard to learn, right? What we now see is that for the integrable part, the locality basically does not affect your final answer at all. That is to say, a very local quantum system can still learn an quote unquote easy system. But as you go to some chaotic or hard to learn systems, the locality decreases what your final distance from an actual answer is. The TVD is the distance from an actual answer. And I want to focus on this blue line, which corresponds to a fully connected classical Boltzmann machine. As you can see, a k-local quantum Boltzmann machine can get to the same accuracy as a restricted Boltzmann machine, which is to say that we can make things easier for ourselves by taking something a little k-local. But this isn't a parameter that you can learn as such. This is something that you have to guess at by yourself, which is why the first line that I came to at the starting of my presentation was locality should be a hyperparameter of your machine learning algorithm. So yeah, this is just the same thing that I was talking about. And so just to conclude what I was saying, SQRBMs are just a very integrable, a trainable, and a performance guaranteed form of quantum machine learning, but they don't talk about locality at all. So when you think about locality in the sense as can I change locality without sacrificing the trainability, and our research says yes. So yeah, thank you. And
Thanks. Are there any questions?
Really fascinating what the machines can do these days.
yeah, absolutely.
I have a question about, suppose I train a machine to detect if a large number is prime or not.
Large number is prime, yeah.
Okay. Then you will have a Hamiltonian.
Okay.
So can you look at what is the meaning of that Hamiltonian? How come you say
Yeah.
it knows how to detect?
Right.
From the structure of the Hamiltonian, can you say what it is?
Right. So basically in terms of the Ising chain that they look at, when you look at the values of the Wij, the weights regarding the interactions, their sign can tell you some things about this, like which two numbers are more probable, let's say. So if I'm trying to train something, whether it's prime or not, the value of W's is going to tell me whether this is a prime or like what is more likely to be a prime in all of the number line, let's say. Right.
Suppose I have trained a machine, which is a perfect
Yeah.
prime number finder.
Right.
So it will have a beautiful analytic form of the Hamiltonian.
Right.
So what is the meaning of that?
So it's going to look at the patterns that correspond to a prime number, let's say.
Right, it's going to, but what
Yeah.
I'm saying, suppose I found the Hamiltonian.
Yeah.
I give you the Hamiltonian.
Right.
Can somebody tell me it's going to detect prime numbers?
Sorry, can you repeat?
The Hamiltonian is capable of detecting prime numbers.
Right. So I think that's the black box part of machine learning coming through. I'm not sure whether just looking at a Hamiltonian I can tell you whether it's
What it's capable of.
yeah. It's just when I numerically go through the results, I can show that it goes down and actually learn something. Right. This is not an explainable AI if that's a part of your question. Right? It's just that you can go on to learn about some patterns of the system at max, but you can't learn how the machine went through all of this process, let's say. Right? Thank you.
So, in these RBM models that you have, if I understand correctly, the hidden quantum variables are actually not interacting mutually within themselves.
Yeah, they
They are
not.
interacting only with
The visible units.
classical guys.
Yeah.
And that makes the computation of whatever.
The
probability
training part easier. Yeah.
So, but if these hidden quantum guys were interacting, how would your advantages or whatever
Right.
special features that you seem to have obtained
Right.
would be affected?
Yeah, so that's a very good question because that is exactly something I'm working on. One of the things that will change is the system is no longer going to be independent or Poissonian now. You can increase the strength of the intra-layer connections and show that it goes to Wigner-Dyson, let's say. So first of all, the training is going to be get a big hit, but we're going to move towards that edge of chaos regime. And there are some papers out there which claim that the edge of chaos is necessary here. So I would expect that in that case, if the training is possible, this number would increase. You'll have something which is more than 3. That's something I'm working on, but the results haven't really been coming out yet.
So you're saying it will qualitatively change from Poissonian to something?
Yeah, that has been shown. That I can show. Yeah.
Okay, thank you.
Are there any more questions?
if not, let's thank the speaker and in fact all the speakers of this session.